Good morning, ladies and gentlemen. My name is Wen-Ta Tsai. I come from Taiwan. It is a great pleasure and honor for me to present the plenary lecture, especially for the first time in the 19th International Conference on Materials, Methods, and Technologies. Yeah. I would like to mention my grad students, Yang Junjie, Cheng, Qilin, and Linda Wei. They are my graduate students. They made a lot of contribution on today's presentation. The topics of my presentation today is on metal feeding into high aspect ratio nano-holes employing supercritical carbon dioxide fluid. I think the use of supercritical carbon dioxide fluid as an electrolyte, I think is novel and is very interesting. I'm very happy to share our experience with you. As most of us are aware that metal feeding into a small trench of wheels with metals is a key technology in the modern superconductor industry in the manufacturing of three-dimensional integrated circuit. And if the holes or the trench is shallow and with the hole diameter is large, dry processes such as physical vapor deposition or chemical vapor deposition can be successfully applied to fill the trench or holes with metals such as copper, nickel, and other metals for electric conductivities. But in the case of downsizing the integrated circuit, the size of the trench becomes smaller, the diameter becomes smaller, and the aspect ratio increase. Then the advantages of using dry process may not be very successful. In that case, wet process such as electroplating may prevail. But even for downsizing to increasing the aspect ratio, then even wet process using electrochemical deposition may not be successful because incomplete filling or the formation of cavity stir occur. In such cases, the use of other technique such as supercritical carbon dioxide containing electrolyte may be useful, and that is the subject I would like to share with you today. And because when we use electro deposition with the aqueous electrolyte, the hydrophobicity is probably a problem. But the supercritical carbon dioxide has a very low substantiation. Maybe it is advantageous for fitting the metal into such kind of geometry. I would like to first to give you some background information regarding supercritical carbon dioxide fluid. I think, in fact, in theory, all material can exhibit supercritical state. Two most famous supercritical fluids are water and the carbon dioxide. For supercritical carbon dioxide, water has been successfully used for power generation to increase the electricity generation efficiency and to reach, sorry, I'm not very familiar with this. To reach supercritical state for water, the temperature should be as high as 647 degree Kelvin, and the pressure should be higher as 221 bars. Okay, but for carbon dioxide, it's easier because the supercritical state can be reached almost ambient temperature with a pressure as low as 74 bars. It's not very difficult. And for supercritical supercritical fluid, they all exhibit gas-like diffusivity and liquid-like density, and especially they exhibit low surface tension for the supercritical carbon dioxide, especially, and also high hydrogen solubility if supercritical carbon dioxide is used. Because of this, so supercritical carbon dioxide fluid has found several applications such as extraction, separation, chemical reaction, particle formation, wafer cleaning. In 2002, Professor Masato Sone in the Tokyo Institute of Technology. He first introduced the electrode deposition into bulk surface by incorporating supercritical carbon dioxide. This technique has been successfully established in my laboratory, and we use this technique not only for electrode deposition, we can also use electrode deposition for a lot of surface modification purposes and many others. And today, I will focus on a new application of supercritical carbon dioxide fluid for metal filling into micro and nano holes. This is a schematic diagram showing the apparatus for electrode deposition. It's not uncommon. It's similar to the normal electrode deposition process. Commonly used the ambient condition. We have an electrolytic cell here. The only difference is the incorporation of CO2 pressurized with high pressure pump so that we can introduce supercritical carbon dioxide fluid into the electrolytic cell, and we perform electrode deposition, electroplating, and even electroless plating in this electrolytic cell. And this technique has been successfully in many applications in our laboratory, and I'd just like to summarize a few of the examples here by using nickel electrode deposition as an example. These are nickel films formed in aqueous electrolyte, namely in ambient pressure. And this is the one we deposit the nickel using supercritical carbon dioxide, and this is emulsified. As we can see from this picture, the surface appearance is different. And the surface roughness measurement indicated that the very smooth surface can be achieved if emulsified supercritical carbon dioxide base is used. And in addition, because hydrogen can be dissolved in supercritical carbon dioxide, the solubility is extensive. So the formation of hydrogen bubble hydrogen gas in conventional electrolyte can be avoided when the supercritical carbon dioxide base was used. In other words, almost the pain-free deposit can be formed in this new process. And the advantage of using the supercritical carbon dioxide can also be visualized from the micro-hardness test. In this figure shows the hardness of the nickel deposited using the conventional process is about 300 or 400 HV. But if we employ supercritical carbon dioxide fluid for electrode deposition, a substantial increase in micro-hardness can be obtained. The hardness can be increased as high as 2 times higher than that of the normal electrode deposition process. And because of the pinhole free and also the change of the characteristic of the deposit, the corrosion performance of the coating in hydrochloric acid can also be differ significantly, as can be seen from this EIS measurement. From the electrochemical impedance spectroscopy measurement, we can see that the impedance for the supercritical carbon dioxide deposited nickel has a very high polarization resistance, indicating very high corrosion resistance compared to that with normal deposition at ambient pressure. So we would like to apply this. We'd like to find a new application for supercritical carbon dioxide deposition, because as I mentioned earlier, that supercritical carbon dioxide has a unique property that is low surface tension. We would like to use the low surface tension. See, it is possible to increase the filling of metal into micro holes with high aspect ratio. In the first study, we used the sintered aluminum oxide as the substrate, and the micro hole array was prepared using a laser drilling. And the characteristic dimension of this cathode or this electrode is shown in this figure. The hole average size is about 50 micron, and aspect ratio was 8 in this case. And we employ the electrode deposition using conventional process and use the supercritical carbon dioxide process, as we can see from this figure. In conventional process, the feeding, in this case, we use nickel phosphorus as the deposition metal. We can see that the metal can only be filled into the cavity, only small amount. If we increasing the pressure for aqueous base, improved deposition was found. However, we still can see some cavity or some defects from inside the cylinders. A significant achievement of filling the hole with supercritical carbon dioxide, it can be seen from here. Okay, so this result indicated that the supercritical carbon dioxide is beneficial in the filling of metals in very, very small dimension holes. Then, because the previous one was studied for micro holes, what will happen if a nano-hole is the goal? Because now the downsizing the integrated circuit is a trend. So how to fill the metal into a very, very small dimension nano-holes is of interest. And I'm going to present some of the data later. And to prepare the cathode electrode, we use the anodized aluminum oxide template for this study. This slide shows the surface morphology of the AO template for the anodized. And we can see the parallel, very fine holes can be formed from the cross-section micrograph of this slide. And with this as a cathode, and we use the electrode deposition process as mentioned before, as shown in this slide and example. We can see in the AAO template as anodized, we can fill some kind of metals. In fact, this is copper into the narrow field. In the narrow sized hole, indicated that even for a hole as small as in the size of narrow older, we can still successfully apply supercritical carbon dioxide for filling the metal into such kind of cavities. To compare the difference for conventional process and the supercritical carbon dioxide deposition process, this slide shows that for constant current deposition condition for a 60 minutes deposition time for the conventional process, we still can find some copper filled into the holes. This is different from what I mentioned for the micro holes, for the micro hole. But as shown in this slide, that by increasing the deposition time, the length of the metal filling into the cavity increases, but a significant increase or a higher filling rate was found in the supercritical carbon dioxide fluid. But the question now arises. In our previous study, we found that the metal filling is not possible in the micro hole. Then what happened for AO template was used as a cathode? Probably has something to do with the hydrophobic or hydrophilic nature of the substrate characteristics, and so that is the next issue we are focusing and will be presented later on. In other words, whether the material properties or the hydrophobic natures affect the deposition, or the difference between the conventional process and supercritical carbon dioxide electrode deposition process is not so different. So we are trying to see what is the main reason for such kind of observation, which is not an aspect. But I'd like to mention here, because in the previous study we used the sintered aluminum oxide as the electrolyte, but for the nano-sized whole filling, we use as anodized AO because as anodized AO was prepared in aqueous solution. Probably the aqueous preparing process result in a different microstructure, different micromaterial properties of this template, and that is the subject to be investigated. And so we applied heat treatment to see what kind of difference can be observed. This is the anodized, this is the X-ray diffraction patterns for the anodized, this is the amorphous structure. But once we heat treated the AO temperature at 860 degrees Celsius for 24 hours, resulting in the crystalline, the phase change, resulting in the crystalline materials. And because water or aqueous environment was used for preparing AO, so several function groups such as OH or CO oxalic function group may exist in the AO prepared from aqueous environment. So we heat treated the specimen and we see the change of the OH functional group as well as the change of the CO oxalic group. So the microstructure and the composition of the AO may change if heat treatment was applied. And the microstructure observation was also performed in the left-hand side. This is the anodized tip and microstructures at high magnification. We can see that the wall, this is the wall of the AO. The thickness is about 53 nanometer average, and the tunnel or the pore size is around 33 nanometers. But if we heat treat this at 800 degrees Celsius for 24 hours, we see a significant change in the morphology, appearance, and also the change of wall size, wall thickness, and the pore diameter. For heat treated, the wall thickness decreases shrink, but the pore size increased to 65 nanometers in this particular case. So not only the chemical composition changed, but also the microstructure also changed with heat treatment of AO. And with this, we then perform the electrode deposition. And this slide shows the result for the heat-treated AO template, but performed in conventional ambient pressure condition. We can see from this is the TM image of the template. This is the PD for the conducting the seed, and we didn't see any copper filling into the gaps in this particular case. Okay, it indicated that if the AO template was heat treated at the high 100 degrees Celsius for 24 hours, the filling of the nano-holes becomes impossible. However, if we use the supercritical carbon dioxide to electrolyte for copper deposition, we can see that the copper can be successfully filled into the cavities. Yeah, indicate the nature or the nature of the substrate. The substrate is important for the use to take advantage of supercritical carbon dioxide deposition. Because of this, so we believe that the change of hydrophobic is one of the important factors for maximizing the electrochemical deposition using supercritical carbon dioxide fluid. So for as anodized AO, we modify the wall surface by immersing in this electrolyte, try to change the surface tension. And this is the as anodized as low surface tension for aqueous electrolyte. But when we modified AO with these chemicals, we can see a significant change in the hydrophobicity. And with this, we then apply the deposition process again to compare the difference between the conventional processes and the supercritical carbon dioxide electrode process. And this result shows the one for modified, we have hydrophobic, modified electrode. You can see the carbon feeding was not successful. But if we apply supercritical carbon dioxide, successful feeding of carbon can be achieved. Based on the above observation, so we come to a conclusion. That is, supercritical carbon dioxide electrode deposition is a promising technique for metal feeding into micro and nano-sized holes with a high spectral ratio. Especially, the advantages is found for the substrate exhibiting aqueous hydrophobic natures. And with this, I would like to conclude my presentation, and thank you very much for your attention.